Welcome to the first official session of yet another machine learning reading group. I'm your co-host along with Callum. We were thinking of maybe doing a roundtable and quickly introducing ourselves.
Cool. Yeah, it's just nice to see everyone and hear everyone's backgrounds. And yeah, so my name's Callum. I am a research engineer at a place called InstaDeep, where I look into offline multi-agent reinforcement learning. And I did the master's in Edinburgh 2 years ago, which is how I know some of the people on this call. And next, I nominate Joshua Placidi.
Hi guys, how's it going? I'm Josh. I'm a machine learning engineer at a biotech startup, working in kind of like a lot of different domains. So doing some LLM stuff at the moment, historically more vision. Um, and yeah, excited to hear what she's going to present today. Yeah, super excited about diffusion stuff. So I think it should be fun. And I know a bunch of these guys from the Edinburgh Masters as well. Cool. I'll pass off on to David. You want to intro?
Yeah, hi, sorry for the delay. I was on the old link. Yeah, I'm David, also from Edinburgh Uni. I did AI, and now we're building Trident when we're building AI agents to fight scams and fraud. Maria, did you introduce yourself?
Yes, so just for a little bit of background, most of us met at a master's in Edinburgh. So we just opened the floor mainly for three of you to join. But for a quick 10-second intro, Arjun, if you want to introduce yourself.
Yeah, I'm Arjun. I'm working at a neuroscience lab at UCL currently.
Cool. And Miguel?
Hi, I'm Miguel, and I'm an economist actually. I did the master in statistics and a lot of a lot of artificial intelligence. And until last Friday, I was working at the United Nations Agriculture Department, but now I'm going to start studying a PhD.
Amazing. Damiano, if I'm saying your name right.
Yeah, perfectly. Hi guys, I'm Italian. I live in London now. I'm a machine learning engineer in the cybersecurity space, and I do mostly NLP and LLM stuff. And yeah, excited to hear about diffusion in this call.
And we're gonna go with Pascual and then Ben, and then we can start.
So I'm still doing that master's in Edinburgh that everyone has done. But yeah, mainly interested in making generative AI more efficient. Right now I'm working on like token pruning in vision transformers, for example.
Ben, do you wanna give a quick intro?
Yeah, I'm Ben. I went to Edinburgh, to my master's there, along with Maria, Callum, and everyone else. At the moment, I'm an AI engineer, working mostly on like very pragmatic, practical uses of like LLMs. But I also did some research at Bank of America, sort of like a year ago on synthetic data.
Great. Thanks, everyone. I'll let Oshin introduce himself. He's gonna be presenting his own paper from his PhD today. The floor is yours, Oshin.
Cool, thanks. And thanks for coming, everyone. Thanks for hosting, Maria, and hyping it up so much. So yeah, I'm Oshin from Ireland. Also did the same Masters in AI at Edinburgh that like most of the rest of the call have done. Um, Currently doing my PhD in Eindhoven University of Technology, mostly working on like generative modeling approaches to signal processing problems, mostly in medical imaging. So we'll talk about a bunch of that stuff today. And yeah, I'll start sharing my screen now. And I'd like to keep it kind of informal today and like chat through these slides that I've got. So I've tried to make it quite tutorial, like mostly focusing on the more interesting like background theory that builds up to the method that we like put on archive a couple of days ago, because I think that'll probably be more useful to you all, because there's some quite nice background theory here that hopefully you can find ways to use in your own work. So yeah, here's the contents. We're going to start off talking about inverse problems, which is covers quite a broad set of problems. It was a term that I hadn't heard until like a year ago, but in signal processing it's big, and I think you'll all recognize some features of it. Then we're going to talk about how to solve inverse problems with Bayesian inference. We're going to talk about measurement efficient Bayesian inference. I'll go into what that means exactly later. Then we're going to talk about diffusion models, which hopefully everybody's hyped for. I'm going to explain a bit what diffusion models are, just from kind of zero knowledge initially. So yeah, just to bring everyone up to speed, in case people aren't familiar, talk about how to do posterior sampling with diffusion models, so how to do Bayesian inference with them, and then finish on like the work that we did for the last couple of months. So firstly, inverse problems. So it's a very popular kind of problem setting that appears in signal processing, but also in all sorts of domains of science and economics and kind of everywhere. The basic setup is that we have a problem of this form where we get some observations, some measurements. So imagine we've got a sensor. There's some quantity of interest that we want to compute or estimate in some way, and that's x. And we know how x is related to the measurement y. It's through some forward model f, which is called the measurement model. And that might be like a physics-based model, for example, or it could be, for example, a linear model. So we really like linear inverse problems, which are of this form. And hopefully this looks familiar to you. So this is a linear system where x is related to y via some linear operation h with some additive noise. So n is just some Gaussian noise. And this totally describes our model. This kind of model can be used for lots of things. It's commonly used in computer vision for things like in-painting or even denoising if H is the identity matrix. But this can also be used in like physics problems, like H can describe a physics model. So for example, in like ultrasound imaging, which we do some work in at my lab, H can actually describe the wave propagation and relate X would be these tissue properties, so how the heart might look or the fetus or whatever you're trying to image, and that will relate to Y, which is these observed echoes you see on the ultrasound probe through this model in H. And so you can actually describe some pretty complicated physical phenomena with such a simple model. And the reason it's called an inverse problem is because this operation H is not invertible, right? So we can't simply compute our quantity of interest X by inverting H and multiplying it by Y, right? So it's usually a low rank matrix. Often it's really like tall, skinny matrix. So this is not an option. And there are a whole bunch of ways to solve inverse problems that have popped up in the signal processing literature over the last like 50 years. I think you guys would be familiar with some of them, even though you haven't heard of them before. One popular way is to just do gradient descent, for example, and put some sort of regularization on X to help make the problem more well posed. And so when I say well posed, one of the big issues with inverse problems is that there's often multiple values for X that would solve this system. And usually we want one correct one, right? So I think a nice analogy from machine learning for this is overfitting, right? So imagine you've got like a set of points that you want to fit a model through, and you could imagine like an arbitrary number of models that could fit these points, right? You could imagine a super overfit one that's like very complex and janky that might perform weirdly outside the data distribution. Usually we want a nice, simple, like smooth model that fits the data nicely, but is no more complicated than it needs to be. And so we use regularization for that purpose. And the same thing is true in inverse problems. If you want, for example, a sparse image, so one that doesn't have too much noise in it, you can throw an L1 prior on the X variable, you can solve using gradient descent, and you're good to go. So to give an example, this is sort of a classic task from computer vision. It's like in-painting and denoising. So this might be our measurement. It's this noisy fish that's half mathed out. We're looking for this target value, which is this fish. But of course, there's an arbitrary number of possible target values that could actually complete this or that would satisfy this model, because on the right-hand side, anything that's in this target image will get masked out, and so it will fit the observations perfectly. But of course, we're not happy to accept just any image as a solution, right? If the right half was just total Gaussian noise, we would probably say, okay, that fits the model, but it's probably not what we meant when we said, solve this in-painting problem. We wanted some kind of fish back in this right half of the image. And that's something that is kind of complex in a way, because how do you define how do you separate which kinds of images might actually count as a solution to us for this right half of the image versus, say, noise, right? You could use like a smoothness prior, or a sparsity prior, like the L1 norm, but then you'll just get non-noisy solutions to the right half. You won't get like a fish body, right? So that's what we're going to talk about next with Bayesian inversion, right? So Bayes rule is kind of to the rescue here, because Bayes rule helps us define what might count as plausible solutions, right? So we can use a prior, px, to basically define a sort of initial set of plausible solutions to this, which might be, for example, a bunch of pictures of natural images, right? So we're going to constrain the entire space of possible images to just this subset, which is where this probability density function, px, will give high probability. And if we sampled from this distribution, we would just get like natural images. And this would help us constrain that set of solutions that would fit the model to only those that we might be interested in. We can think of it as plausible solutions. Then we'll have our likelihood, and that will basically serve to constrain that initial set of possible solutions to only those that fit the model, right? So our likelihood might look something like this, where we actually represent the Ford model as this Gaussian, where we apply the masking operation in this case, and we say, okay, we can take any images from our prior, but it's going to be narrowed or constrained by this likelihood, so that if we sample from the posterior, computed here, we only get images that both satisfy the model, right? So in that case, that means the left half matches perfectly this fish face, but the right half needs to be kind of still plausible under the prior. So I think that's a nice way to think about Bayesian inference, as like this initial set of possibilities that are then constrained by the likelihood. And you can repeatedly do Bayesian inference, right? So you can get your posterior, and that becomes your next prior. And if you keep multiplying by these likelihoods, each likelihood will further constrain that set. Okay, does that make sense to everyone? I'm going like talking at a million miles an hour here, but I should stop and like check if anyone has any questions. Okay, well, feel free to stop at any point. Now we're going to talk about measurement efficient Bayesian inference, which I don't know if this is like a real term. This is just a term I made up to describe this idea, but we're going to start with like some intuition for what I mean by this. And so I'd like you all to think about MNIST, which I assume you're familiar with. It's these handwritten digits. And imagine a case where you have like a 5x5 square of pixels that you're allowed to see, but the rest of it you're not allowed to see. And you want to figure out which digit is present. So there's some mystery MNIST digit. You're only allowed to look at a small section of it. Which bit do you choose to get the highest probability of being correct? Any volunteers?
Yep. Yeah, I've got an idea.
Okay,
The bit that varies the most, that's like that, you know, that changes the most, or that you can most easily use to like tell the difference between the numbers. So I'm guessing here it would be somewhere in the middle, like maybe middle to the right. I'm not entirely sure where that would be, and I don't know how to put it more formally. But
no, you're actually bang on, Ben. Yeah, that's totally the right idea, right? So imagine you just went in the top left corner, right? Everything would just be black no matter what the number was, so that would be useless. So as Ben said, you want to pick the region where you expect the most difference between different kinds of numbers, right? So here, like the middle would be a good suggestion, I think. Like the bottom might be a bad option, because if you selected the bottom here, you can see that 4, 7, and 9 all have very similar like tails. So maybe it will be hard to tell which one it is, but the middle is probably a good answer. And the key idea is that you want to select somewhere where there's a lot of difference between the possible options. Okay, because the more difference there is, the more information you'll get. And I'll like formalize that a bit in a second, but I think that's a good intuition to start with. So now we're going to take a more practical example than MNIST. Even though I love MNIST, we have to make it like real world applicable at some point. So a good but still quite similar case is MRI. And accelerated MRI in particular, you might have heard of the Fast MRI challenge. This is like an open access data set that you can just download and play with. And the goal is to speed up MRI acquisitions. So MRIs take a long time. And by subsampling the MRI data, but getting still like a good quality result, we can speed that up. So MRI also is an inverse problem, or at least subsampled MRIs. So we have a linear model again. And the way MRI works is you get measurements in the Fourier domain. So you take some image X, you do a Fourier transform, you subsample it by this subsampling matrix U, so that's just a mask again, and you get your measurements. And the way the MRI machine works is you can scan a column of pixels at a time. So each column is basically one acquisition, and the goal is to choose which lines you should select in order to get the most information about this knee MRI or whatever you're trying to image. So one way we can formalize that is we can say, well, we want to be as certain as possible about what this knee image is, so we want to minimize our uncertainty. And similar to how Ben described, we can measure the uncertainty by how different the options might be if we were to sample from a certain region, and we can measure that using the entropy. So this is just the information entropy from information theory, and that roughly says how close to the uniform distribution is it, right? So if it was uniform, you've no idea what you're going to get. That's a high entropy distribution. If you know exactly what you're going to get every time you sample from this distribution, it's a low entropy distribution. So in the limit, it will be like just a single point, like a delta distribution that you just repeatedly sample the same thing from all the time. So here we can just define an objective using this idea of entropy on the posterior. So this is saying, okay, if we use a certain subsampling mask, that will lead to some observations Y. How do we choose that mask so that the observations will minimize the entropy on X? And that will be the optimal mask. And it's popular to solve this objective iteratively. So what this equation up here says is it tries to optimize this mask all at once. So there's this constraint that there can only be K scan lines, but there's no order specified here. You're just trying to optimize all K at the same time. And there's some papers that do this using like the Gumbel softmax. I know we have some Gumbel softmax fans in the audience, so I just thought I'd mention that because you can use this as like a discrete optimization task on the subsampling mask. And yeah, that works quite well. But an alternative option is to do it iteratively, because each time that you take one of these lines, you get some information. And you can use that information to make a better decision about what the next line you should scan is. And so if we formalize that, and yeah, we can use some other tricks that I have in the paper if you're interested, but we can actually show that something that's equivalent to minimizing the entropy over the posterior is actually choosing which lines would give the maximum entropy in the measurements, right? And this kind of matches what we were talking about earlier with this the region that we expect to be the most different, right? So in this case, in order to minimize the entropy of our target image, we want to maximize the entropy of the measurements we expect to get. Okay, so very different measurements lead to the biggest decrease in entropy in our target distribution. And so yeah, this now turns into this iterative process that can be kind of seen like a planning problem in a way, right? You've seen some observations so far, and you're trying to make the best decision about which one to sample now. So how do we model this, right? H is just this like mysterious symbol here, but we want to actually be able to compute it to solve this problem. So the way that we chose to do this in our paper was to make a sort of empirical estimate of the distribution of YT given the previous Y measurements. So this is kind of the simulation step, right? So you've seen these T-1 lines so far, and you want to simulate what are all the possible things you might expect to see at any given point that you might sample, right? And we simulate n of those, so then we get n points in the measurement space. So in the case of MNIST, these might be n different possible digits we would see. In the case of MRI, it would be n different possible Fourier measurements we'd see, and so on. And we just plop Gaussian blobs on each of those points, and that gives us a Gaussian mixture model. And we use a Gaussian mixture model because it's easy to compute, or well, approximate the entropy of a Gaussian mixture model. And that gives us our like quantity of interest that we can optimize. And it's actually very simple to do this entropy approximation. You just look at the L2 norms between each pair of points in that space. So all your possible MNIST digits, you just compute the pairwise L2 norm between all the pixels. And wherever there's a high average L2 norm or like max L2 norm, that's a place where there's a lot of disagreement and high entropy, and that's somewhere you want to sample. So it perfectly aligns with the kind of intuition you'd have about this problem if you just think about it for a few seconds. So any questions about this?
Yeah, What's YT again? Can we just go over the?
Sure,
Is
yeah.
that- yeah.
So I'll actually just go up to, maybe I can show you a GIF for this. So there's going to be some spoilers here, but I think this will help. So YT, you can see here in this measurement mask, it's kind of evolving over time, right? At certain points, we're like adding a new scan line. And so T is just the current point in time in this process. So what we're trying to do is we're trying to, at any given point, we've got like a bunch of lines we've seen so far, and we want to choose the next one. And so we have line 0 to T minus 1 are all the ones we've seen so far, and we want to choose line T. And once we've chosen it, we kind of process that information, and then we choose T plus 1, which becomes T. Does that make sense?
Yeah. So yeah, I guess at any point it would be a value of like, well, I don't know, something on the x-axis. Is that more or less
Yeah,
correct?
exactly. Yeah, so
Um,
it's actually the measurements themselves in this case. So it's actually what you would see if you did that measurement, right? So here, this kind of corresponds to the measurement mask. So this is like if we were to multiply this by our image, we would see all the pixels that have a white line in front of them. So in like the MS example, it would be what you actually see in that little box, right? So it would be like a tail of a number or whatever. That's what Y will be.
Okay.
Rather than the index of the pixel. Yeah. Okay. Any other questions, or will I move on to diffusion models?
Yeah, can I ask one quickly? Can we go back to the GIF for a second?
We can go back to the GIF.
I love the GIF. It's I know it's jumping ahead, but so here the model chooses to sample a lot from the center of the image, like the measurement mask, are all very tightly clustered. That's based on a prior that there's kind of like what Ben said with the MNIST is. So there's this prior, and then from what it's seeing, it's deciding where to further search. But it seems like it's always very. Is it common to see the measurement mask be so centrally?
Yeah, good question. So this measurement mask is in the Fourier space, right? So the way it's plotted here, it looks kind of like it's a mask on the image, but that's actually a mask on the Fourier. So the center of the Fourier space for images corresponds with like low frequency components of the signal. So that's all the big shapes. And then the bits on the left and right at the extremes would be like very high frequency components, like the little noisy details on the texture, you could say. So in MRI sampling, they always sample the center a lot, even for predefined masks that like experts have designed, because there just is a lot of information in the center. About the relationship between the prior and the mask that's chosen. So we don't have any prior on the mask itself. The prior is just on the data, and then the mask just emerges according to wherever the most entropy is. So in this case, when the model has no idea what the image is going to be, there's going to be the most difference in these lower frequency regions. So like the shape of the knee initially will be very entropic, and so sampling in the middle will like disambiguate the shape, and then it moves on to the like finer details later. So yeah, does that make sense?
Yeah, actually that clears up a lot. Thanks.
Cool.
Can I ask one more quick question? I think I'm nearly completely on board. I just want to establish one more thing. Could you just go to the equation from before?
I can.
Yeah, okay. Yeah, so for this one, you see where you go use the set of simulated possibilities. So I guess
yeah.
So this is how you pick, which one like, say you want to know which line on that GIF we were just looking at to sample from. You want to find the one with the highest entropy.
Yeah.
So is it going across all of them and then predicting n possible values for each one and then picking the one with the highest entropy?
Is
that okay? Cool.
So each line gets an entropy. So if you were to imagine like brute forcing this, right? You could just do a for loop over each scan line location. For each one, you simulate all the possible measurements that you might observe there, and then you compute all the L2 distances, and you get a number which is entropy for that scan line. Then you go on to the next one, and so on, and then you get an entropy for every scan line, and you just pick the one that's the max, and that's where you sample. That's the idea.
Cool. Yeah. Okay.
There is a more efficient way to do it, which we'll get onto later, because that sounds kind of inefficient to do all these simulations for every scan line, but you can
By the way, sir, just to make clear, scanline here equals to one frequency that you're using the sampling with. Scanline equals frequency that you're sending into the MRI.
Yeah, exactly. It's a whole column of pixels in the Fourier space.
It is in the Fourier space. Okay.
Yeah, it is.
So it's in the frequency spectrum. Yeah, okay, makes sense. Yeah.
Looks like this. If you were to have a mask that matched this, you get something like this as your measurements.
Makes sense.
Yeah. Okay. Thanks for all the questions. So I'll move on now to diffusion models. But if there's any more even questions about like prior stuff, like feel free to interrupt and we can just chat about it. So diffusion models, everyone's talking about them. They can be useful for solving inverse problems like this one, which is nice to see that there's some applications in like science and engineering, as well as making cool pictures. So if you have no idea about diffusion models, here's sort of an initial idea. You start, you've got this forward diffusion process, which repeatedly adds noise to clean images. So these start off as images of beds, I think, and it's just iteratively adding noise. And eventually you end up at total like white Gaussian noise. And you can see this reflected on the right here. We start with the structured distribution, right? So this is meant to be like the distribution of natural images, but here for illustrative purposes, this is just like a bimodal Gaussian. The point is it's some distribution that's slightly complex in some way that we're interested in learning. And by adding noise repeatedly, you can see that each of these is an individual sample. So you can imagine each of these points as an image initially. We repeatedly add noise and we end up at samples from just a standard normal Gaussian distribution. And what we would like to do is learn to reverse this process so that we can start by just sampling some random white Gaussian noise, apply our diffusion process or our reverse diffusion process, whatever that might be, and this will give us samples from this structured distribution. So here it goes from Gaussian noise towards the nice pictures of natural images. And so there's this interesting connection between noising and denoising and probability distributions. And I think that that's one of the cool things about diffusion. These are two things that seem kind of unrelated, or at least they did to me anyway, but there's a very nice link, which I'll describe in a second. And one thing that's really nice about diffusion models is that their training objective is super simple. So it's about as simple as this. You just take a clean image from your training set, you choose a time point in the diffusion process. So this just corresponds with how much noise you're going to add. So if it's very far on in the diffusion process, you add a lot of noise. If it's at the start, you don't add too much. And you train a neural network to take that noisy image and the noise level as input and try and predict the noise that was added. So there are many different ways you can train diffusion models, but this is a popular one. You can also train it to predict the image, but predicting noise seems to work well, like empirically. And once you predict what the noise was that was added, you can just subtract that from your image and you get your clean image. So we literally just train a denoiser. Then to do inference, you can repeatedly apply this denoiser with some extra like scaling terms and stuff, and you get eventually to your clean images, right? But I'm not going to go into too much detail. There's a bunch of really nice papers that I can link. I have some in like the references at the bottom here. If you want to go into like the diffusion maths, it is kind of a bit like verbose, but it's worth doing if you're interested. But what I'd like to talk about is the relationship to probability distributions. So the link is that we can directly relate this predicted noise to what's called the score of the probability distribution. The score is the gradient of the log probability. You might recognize this from the PMR course in Edinburgh, since there's so many Edinburgh people, the method score matching. It's the same score as score matching. And what that gives you is like this vector field that basically from any point in a space, it points towards regions of high probability density. So if your probability distribution looked like this, where there's some peaks here that are very likely, then if you plotted the score, you'll get arrows pointing towards those peaks at any point. And that's really useful for sampling from a probability distribution because you can use this to pick some random point in the space and then just compute the score at that point, and that gives you an arrow, and you can just move in that direction and then compute the score again, and you'll get a new arrow. yeah, just a perfect path towards regions of high probability density. And then after you've done a certain amount of steps, when the gradients start to like get smaller, for example, or you reach sort of a local optimum, you can just stop there and you hope that this point you've landed on is like a nice image, because it should be at a region of high probability density. And so because this denoising neural network function that we've learned is related to the score in this way, so in particular the score or the noise is like the negative of the score, right? Because the intuition for this is that if you add noise to a sample, it will move you away from regions of high probability density. And so by inverting the noise, you'll move back towards regions of high probability density. And yeah, you can use this like Langevin sampling algorithm. It's called, which is basically just gradient descent with some added noise, so that you don't get stuck places. And if you do this, you can start at a random point, repeatedly add the score function with a little bit of noise for like randomness, and stop according to whatever stopping criterion you have, and you get samples this way. And this is how people sample from diffusion models, or this is like one of the interpretations. So does
Sorry.
that make sense?
The epsilon, there's the noise, is it?
This is
That-
other noise. Yes, this is kind of badly
Yeah.
written. But
And then
this
C?
is not the same noise that was added.
Yeah.
This is just
Before.
other. Yeah, exactly. This is not the noise that was added like during
That's just
training.
like an exploration.
Literally,
noise.
yeah. Literally, it's like an exploration term. And you
Okay.
can remove that if you want. But yeah, you can see on the plot here that the points we start at, let's say if we start at a point here, they don't just smoothly go to, or I don't know where we started
Yeah.
actually. These are, but if we started and we just followed the score, we'd get like this smooth trajectory towards the peaks.
Yeah.
But by adding some noise, we increase the chances that we'll end up on other peaks. I mean, you also start at an initially random point, so yeah.
And
but
C there?
C is like a scaling term. So this is
Oh,
just a bunch
okay.
of like 1 over root 1 minus alpha bar
Oh,
stuff.
cool.
Is like painful to look at. So yeah, it's just proportional to the score basically. You basically change that term as a function of which noise level you're at. So you start at Gaussian noise and you assume that you're at like a high noise level, and then the score function, you can see that the epsilon here, the denoiser, it takes T as an input. So depending on the noise level that you think you're at, you'll have a slightly different version of the denoiser. So this is just like a scaling term that corresponds. But the main idea to get across from here is that the score just points you towards the prior. It just points you where you need to go. There's like a bunch of maths you can go into and like nice papers on it, but we don't need it for this. Okay, I'll keep going.
This is a super interesting way to formulate diffusion. I've never seen the inference sort of done like this. It's really interesting.
Yeah, there's like so many different ways to look at it. There's a nice paper called like a unified perspective on diffusion models by this guy Calvin Luo, who I stole this picture from. So shout out to him. And it shows you how to like you can define diffusion models as a sort of form of a hierarchical VAE, where you just stack a bunch of VAEs, but you make the encoder just be a noising operation, and then it becomes a diffusion model as well. So there's like a bunch of cool ways to look at it. I'd recommend that paper. Okay, I guess I'll keep going. I think most people are back. So the next thing, now we've figured out how to learn this probability distribution with diffusion models, but we're particularly interested in posterior sampling. So not just learning px, but learning px given y. So if we observe some measurements, how can we tweak where we go so that we find something that has a high likelihood under the prior, but that also fits whatever model we have, or like solves whatever problem we're trying to solve in our forward model. So that's where this method, diffusion posterior sampling, it's called, comes in. So there's a nice paper, diffusion posterior sampling for solving general noisy inverse problems, which is what I describe here. So if we go back to this idea of the score pointing us in the right direction, we can look at the posterior score function as the sum of the prior score with a likelihood score. And so we know how to compute this prior score. That's just a diffusion model like vanilla, but we need to figure out how to compute this likelihood score. And the likelihood score that we have a model for, it will look something like this if it's like Gaussian. So it'll just be like the L2 distance between your model times like the x. So in this case, it would be like, if it's like the MRI example, you compute like the Fourier transform, you compare it to the observed Fourier, and you want to minimize that distance. Typically, if you're just doing like maximum likelihood estimation. But the problem is that this model is defined for a denoised x. So x0 here corresponds with like a clean x image. But when we're doing diffusion, we have these xt's, which are noisy x's. So t indicating like the time point in the diffusion process. As t goes towards 0, it gets less and less noisy, but we can't just put a noisy image into our Ford model here. We need a clean one. And so the trick that they use for diffusion posterior sampling is to use this thing called Tweedy's formula, which lets you compute the expected value of the clean image given a current noisy one using your score function. So this is like you're at some noised image and you want to come up with your best estimate of what the final clean version will look like from where you currently are. So the diffusion model typically does this iteratively to like make its way towards a nice solution, but you can come up with a rough guess of where you'll end up via Tweedy's formula. And you can see that this is just like a scaled version of the score function. So this is like you take your score, it points in some direction, and you just go all the way to the end in that direction, rather than moving step by step. You just jump all the way. And then you get this expected value. And so what diffusion posterior sampling does is it uses this estimate in the Ford model. So this might be like our MRI measurements that we've estimated. It'll be our MRI image that we estimate. We put that through the model, compare it to what we've actually observed. So these measurements Y, these are some actual observations that we want to fit. And we can take gradients then. We can backprop through the score function through the diffusion model all the way back to that point we started at, that partially noised image. And we can say, how would we move this point such that the Tweedy estimate, so the estimated clean version, would be closer to something that would fit our model. And yeah, so, okay, I see some confused faces. I'll explain that again. So from some noisy point xt, we can estimate what the eventual clean version will be. And when we have a clean version, we can put this in our model. And we can get some information about how good it is. If it's a good clean version, it'll give us a low L2 error here. If it's a bad one, it'll give us a high, right? It'll be like low likelihood or high likelihood. And we can, because this function here, this score is just our diffusion model, it's a neural network, we can just backprop through this whole thing back to that noisy XT image and say, well, if we changed that a bit, it would have then resulted in a Tweedy estimate that would have better fit our model. And that's the direction we want to go in. Does that make sense? Yeah, maybe this is also just one to like think about a little bit. But if anyone has any questions, please ask. The basic idea is just that this function, this score, likelihood score, tells us where we need to move to eventually get solutions that will fit our model. That's like the main thing to take away from that. So it's another arrow, right? We've got two arrows now, one for the prior, one for the likelihood. And the way we do diffusion posterior sampling is then we just iteratively take one step towards the prior, one step towards the likelihood, and so on. And this leads you towards points that are both likely under your prior, but that also solve the problem. And like, here's some examples of in-painting for that. Any questions? Okay, I'll move on to this is now the last point, so we can get to discussion soon, which will be more fun maybe. So this last slide is on the method that we introduced, which is active diffusion subsampling. So this tries to solve the problem that we discussed earlier, where we get to pick what that mask is. So typically in all the diffusion posterior sampling type literature, they just assume some mask, like, you know, a box is missing from the center. But often in like science and engineering, it's up to you to choose the mask, and, you know, in MRI subsampling, for example. So now we can like return to this model of the entropy that we discussed earlier, and the diffusion models fill in this simulation gap. Yeah, Ben?
Sorry, just quickly. So I didn't understand the part where you just said, so in science and engineering, you can choose the mask. So is that like you choose the distribution that you think it actually is, or am I missing?
So by that, I literally mean that you get to pick where you measure, often in science and engineering. So
Right.
in a lot of the benchmarks that they use for like
Oh,
these diffusion models, they'll just pick some random mask or like a box in the middle or something that's kind of meaningless. But in something like MRI, you actually get to choose where you scan in the Fourier space. And so if you can use a diffusion model to also figure out where to scan as well as solve the problem, um, that's kind of handy. That's basically the idea.
cool.
So that's the problem that we try and solve with this method. And the diffusion model particularly comes in this step one, where we're trying to simulate what we expect to see in different regions given what we've seen so far. And what we do is we leverage this Tweedy formula that's already used in diffusion posterior sampling. So if you're just doing regular posterior sampling, you'll get these X zeros along the way that are predicted via Tweedy's formula. So these are like the points that you expect you'll end up at when you've fully denoised. And we can use those to simulate the measurements that we expect to see at different points. So I think this graphic will help explain it a bit. So we start off with some kind of noisy version of the image. This is like another knee MRI, and we might have a whole batch of points that we're like denoising at the same time. So each of these points is some alternative possible noisy knee image that could maybe fit our model. Like nothing's ruled it out yet. So these are kind of the open options. And then we use Tweedy's formula and we get this clean estimate, which it's not going to be perfect, but it's an estimate. It's like this expected value of X0 given the current noisy one. We do that for each of them. And so we get this set of like simulated end results that we can then put through our forward model to get measurement points. So this is just a Fourier transform, and then we get into our measurement space. We get these points in the measurement space that we put the Gaussian blobs on, giving us this Gaussian mixture model. And then we can just compute the L2 distances between all these points and figure out what the entropy is for each line. And then here we just pick the max line, and this gives us a new measurement. So I think maybe it's a good way to talk about this is like, forget about the Fourier, imagine it's just MNIST again, and we're just trying to pick which region of MNIST is most entropic. Then our forward model is just the identity matrix, right? We don't need to go into Fourier space or any other fancy measurement space. It's just the pixels. Then we would start off with a bunch of noisy MNIST images that we would denoise by this Tweedy estimate, and we get kind of a belief distribution, you could think of it. So this is the set of things that are still options that we haven't ruled out via observing some evidence to the contrary. And then we literally just, our measurement space is the same as X. So then we just look at all those possible elements in the belief distribution. We look at where it differs the most and we sample there. And then when we get that sample, we can use that. So we take that sample, we do some more diffusion posterior sampling steps. So we kind of ingest that information, we update our belief distribution, and we get to a new set of noisy points. And then we can repeat that process. So, by observing some measurement, we'll rule out some possibilities in our belief distribution. That'll narrow a little bit. And then we'll be able to simulate, okay, now what do we think the measurements will be? And we'll get another set of entropies, choose another sampling location, and repeat. And that's what you see going on here in this GIF. So at tau equals 0, so at the very start of the diffusion, we've no idea what it'll be. We get these like weird noisy estimates. The Tweedy estimate's really bad because the images are very noisy. So that's why you get these like weird blurry images at the start. Then we do some measurements. We improve our estimate. Now maybe a lot of the low frequency information is known. So it starts trying to fill in these high frequency details, like the surface texture, take more measurements and so on. So this is like the belief distribution updating over time. This is the final mask, and here's the prediction. And that's basically how the method works. We like in particular, like one way of thinking about this is you can have like an agent-based interpretation where the model is an agent. It has this belief distribution. It has this goal, which is to find out what the final image is, to get as certain as possible about that. And its action space is the set of sampling locations. And what the diffusion model does in this case is it simulates the entire action space. So because subsampling is kind of a pretty small action space relative to like other problems you might try and model with agents, by simulating just a standard image, we actually have simulated the results of all the possible actions, right? Because all we can do is sample different points in the image. So by simulating all the pixels, we've actually simulated the outcomes of any action. And the reward function then is just the expected information gain. So there's kind of this agent-based interpretation as well. Does that bit make sense? Or would anyone like me to explain anything further there? Cool. So one last GIF. We also tried it with stable diffusion. So one nice thing about this method is that you can just pull like a pre-trained diffusion model, and all the values you need are pretty much computed anyway. You just need to add some of these entropy computations on top, and it just worked out of the box. So here's a case where we just gave it this face image, and we were like, okay, you've got this many measurements you can take, and it designed this mask that like you can see kind of resembles a face. You can see here as it's going, these are the Tweedy estimates. So this is what its prediction of where things will end up. And you can see by now it's figured out that it's a face, but it's not sure exactly what the face looks like. So it tries to sample like particularly around the eyes and mouth, because that's where the most difference ends up. Like the forehead, once you know like the skin tone and so on, there's probably not that much information there. And this is the final mask it comes out with. So yeah, that's the presentation basically. I know it was 51 minutes, so that's probably way longer than you all expected. So thank you for bearing with me. Some future work we'd like to do is just, get rid of assumptions we make, look at different kinds of general models, look at temporal inverse problems. So where you have like a video, or like we work with ultrasound a lot. So ultrasound is a video, and that's quite nice because you can use like prior information about what happened a few seconds ago to decide where you should sample and so on, and speed up inference. So one bad thing about generative models is that, or diffusion models in particular, is that they're kind of slow. So for real-time applications, that's kind of a problem. So yeah, and then I think some like broader context or discussion points. I know agents are very popular in machine learning at the moment, and I think that, in particular, as I mentioned a few minutes ago, you can look at this as an agent-based planning problem where the reward function is expected information gain, and that's kind of nice because in a lot of these planning problems, I don't know if anyone saw, there was a recent paper that like Kevin Murphy published called like what type of inference is planning, and there he talks about how you can do planning as a type of inference, kind of like Bayesian inference, and a lot of the terms are entropy terms. So having the reward function also be an entropy term is kind of nice because you can cancel some things out, and I think it's kind of interesting to just implement these like information seeking agents. It ties into like the Carl Friston free energy principle stuff, and I think a lot of people are trying to make that happen. From an engineering point of view, like the theory's out there. If anyone hasn't heard of this free energy principle, it's like this grand theory of intelligence in one equation that I think is gaining some traction in AI at the moment, and it's all about maximizing information gain. So worth a look. Final point is that I think if we wanted to make this about LLMs, I think there's an interesting like analogy here where imagine you had an LLM that's talking to someone and it's trying to get as much information as it can from that person. And its goal is to find out an answer, or find out some information from this person in the fewest possible number of questions, or the lowest possible number of questions. You might get the LLM to simulate what would happen, what the response to a certain question might be by the person, and then eventually choose to ask questions that it thinks will lead to a wide variety of responses that might be very like information dense. Okay, I'll leave it there. I guess we can open the floor a bit now to some discussion.
I really like the use case about minimizing number of questions. Very applicable to Trident.
Yeah,
and of course, great talk. I think we need to start with that.
Talking to you about it a couple of weeks ago is what made me think of this. But I Googled it, and someone has done something like that for recommender systems already, actually. Like not like what Trident is doing, but to try and figure out somebody's preference about like a product in the lowest number of questions. I didn't look at the method, but it's something kind of similar to what I've been talking about.
But here you would need to swap the diffusion model with the LLM or some kind of model like that who is trying to like simulate like the entropy, right?
Exactly. It just needs to be some model capable of simulating what a person might say in response to a question. So that might be an LLM. I know there's like diffusion LLMs are a thing as well. But yeah, some sort of model that can simulate that. Ben, do you want to?
Hey, yeah, sorry to bring it back again. I think I'm very, very nearly there with this understanding. I don't know where I was 5 minutes ago when you're explaining this part. So I understand sort of like the basics. Could you just go down to the example with the guy here in the because this one was like more intuitive to me. So, okay, so what's the equation that determines where the next square is going to be? And I know this is like I know this is the key point, but like what?
No,
because you said before you weren't going to brute force it, or that was a better way.
The equation is so like in a way we do brute force it, right? But it simplifies a bit because we can simulate the outcomes of all the different like subsampling locations at the same time by just generating what we think the whole image will be. So these like posterior samples here in the belief that's what it is. And you know, for subsample, like for other types of action spaces, you couldn't do that, right? But subsampling in particular, each action is like a mask that masks out most of the image. So you don't need to simulate the part of the image that's masked out because it's all zeros and you know that in advance. So you can do some like maths that shows that you just need to simulate the one image and that's like simulating the whole action space. But if your actions were like, if you had like a robot that was gonna, I don't know, turn a corner or something, it might need to simulate, you know, the outcome of every action individually in order to do that, rather than just being able to parallelize it in this way. But yeah, it's because we know in advance that anywhere that's not in the subsampling mask will just be a zero, that we don't need to simulate all those zeros, right? Like yeah, the brute force way would be to simulate all the zeros as well as the bit that you expect to see every time. That's the like trick. Makes sense.
Cool.
Oshin, there's a link in the comment in the chat.
Oh, sorry, I haven't been reading the chat. Apologies.
I think you're gonna share this paper with everyone, and I see that you have references at the bottom. So maybe the paper is already included there.
So actually, the recommender system paper is not included there. I'll Google this now and find it. Can you guys still see my screen, or did I just share my one?
Just the PDF.
Okay. Yeah. I'll just share the link then.
Perfect. Any other questions?
Yeah, not really a question, but well, yeah, I guess so. So I think this example with the face is super intuitive and it really demonstrates what's going on. I was wondering if you trained it or if you tried any other kind of experiments with different kind of data where you saw things that aligned with what you would intuitively think. So, for example, I'm looking at where it's choosing to select to get information from the face image. And it doesn't necessarily line up exactly with what I thought. Like it's a lot of like stuff going around like the outskirts of the image, whereas I thought it'd be a lot to do with like facial features or kind of for the faces, I've got other data. I know you did some stuff for black holes as well. Did you find any kind of like cool like things that align with your intuition?
So with the face example, the outline is an interesting point to note. It seems that a lot of the difference between these like faces in the top right seems to be in exactly where it draws the boundary of the hair, right? And you might notice the hair is black and the background is white. So that's going to cause a large difference in the L2 norm. And this is kind of to do with how we choose to model the entropy, which is as this Gaussian mixture model. So we just say that something has a lot of information if the L2 norm is high, but that's not necessarily true. So you could model that better. And like the best way to model it would be to like backprop through the diffusion model and to see, you know, you could actually backprop to the mask and then see, you know, if you turn this pixel on, would it result in the posterior distribution getting tighter? But that's inefficient. So yeah, we're going to explore that in future. Like I think there might be some potential there. But to answer your other question, yeah, I've also tried it on ultrasound with videos, and it was interesting to see there that it would scan the lines where there was the most movement, right? So like a heart valve would be opening and closing, And the task of this like agent was to basically compress the video as much as possible, so to get as much information across in the fewest amount of samples. And naturally, the places with a lot of movement are the places you need to scan very regularly, because if something stays the same, you don't need to scan it again. So this also like aligned with our intuitions nicely. But I think we've only applied it to like, yeah, natural images, ultrasound, MRI. But I think if you applied it in other domains of science, I'd expect that you'd see masks emerging that like hopefully align with your intuitions. But yeah, and with the black hole and stuff, it just measured in the area with the black hole in it and not the black space around it. So that was kind of what you'd expect, you know. Okay, more questions from Miguel.
Do you think the same approach can be applied to a time varying X in the sense, for example, of it being the distribution of crime in a city or the opportunities in some type of representation of the stock market that you need to?
Yeah, I think so. So we've tried it with time varying X in the sense we've tried it with video. So like I might have some. Let me just.
You've tried to forecast the next frames of the video.
Yeah. So we've done it with ultrasound, which is a video, and it works quite well. So I don't see why not. I think that it would work even better with like, you know, one-dimensional variables like stock price or something, because then you need less data to learn the diffusion model and so on. And yeah, but in theory, this can work for any kind of probability distribution that you can like fit a generative model for, right? It doesn't even need to be a diffusion model. You can still compute the entropy and everything from like a GAN or like whatever other generative model you'd like.
Have you observed any type of useful rule, thumb rule, or relation between how fast or how many measurements you can take and how fast the video is changing?
This has been for us like limited by the diffusion model inference speed so far. So diffusion models are kind of slow, but in theory, I mean, yeah, this like the more the better, right? Like, yeah, you're going to be limited by your inference speed, I'd imagine. You're either limited by your inference speed or like the sample rate of the signal that you're sampling, you know. But the more the better in that sense, I think.
Thank you. Awesome presentation.
Thanks.
Yeah, thanks. I have to go, but it's been great, and I'll definitely give it a quick read through when you send it out as well.
Cheers. Thanks, Matt. I'm gonna look for that paper that people asked for, by the way, and drop it in the chat, but I haven't been able to find it again.
We can add it to the Notion doc as well.
Yeah, I'll do that.
I think we're gonna leave it here for today. Thanks everyone for joining. We are gonna do this every 2 weeks. The next session will be presented by me, and it will be a little bit of crypto and how we use graph neural networks for anti-money laundering. And the next one will be Josh telling us about what the new Apple Intelligence is doing, all those hidden optimizations that are really cool. And the next one will either be Callum updating us with his 2 recent papers or David telling us about his company Trident for fraud detection. Any words, Callum?
Yeah, I'm keen, but depends if David wants his corporate screen time. I don't know. I'm just a humble little researcher trying to put out open source things to the wide world. No, there's one paper in particular that I'm quite keen to speak about on coordination in offline reinforcement learning. So that should be quite fun.
Josh?
Can I ask one quick question to Oisin that's completely unrelated to his talk? What did you make that PDF in? Like, what was that? Because that didn't look like Notion, but looked very similar to Notion.
Yeah, that was Obsidian, but I just styled it to look
Obsidian,
like
okay. You're embarrassed about using Obsidian rather than Notion and scared of the peer pressure.
I wouldn't say that, but I do actually like this new team, honestly. I'm a lot
more that's cool
person for documents. Yeah. But yeah, it was quite nice. There is a slideshow app like plugin for it, but I found that didn't work so nicely, so I just like scrolled.
I thought that was actually really good to be able to like just scroll through continuously and not have to like jump slide to slide. I thought it worked very well. I'll probably do something similar for mine.
Cool.
And if Pascual, Damiano, Miguel you three are the only ones that didn't join the masters. That's why I mentioned you. If you want to present anything also, we are very keen to hear what you're looking into. Or you know anyone else who would like to present something, also very keen.
Sure, yeah, I'll be down at some point.
I want to hear what you did about Edinburgh AI. Looks really cool.
Thank you, thank you.
Okay. Goodbye, everyone. Have a nice evening.
Thanks,
guys.
everyone.